So really, if you take nothing else away from these sort of 3 hours which I've spent with you talking through Bayesian statistics this week, if you take nothing else away, take away this, okay? It's just a formula, but think about where it comes from, okay? Good. Okay, so, yeah, I'll talk it through on the screen if that's okay, because then it just saves me writing it out every single time, so I can keep that on the board and I can keep referring to it. So you remember yesterday, what example did I start with? It was a thought experiment I started with. Can anybody remember?
The disease.
Yeah, I started with the disease example, right?
Yes.
So just a reminder, so in case you've forgotten or in case you weren't here, okay? You remember that I told you that you go into the doctors feeling really rough, like really ill. They take a test, like take a load of blood tests from you, and they find that you have a disease that affects 0.1% of the population. And you, being a statistician, go, well, hang on a minute, how accurate is this test? And they tell you that the test is 95% accurate, okay? Now, does anybody remember, what was the probability then, given this information? So given that the disease only affects 0.1% of the population, or 1 in 1,000, and that the test is 95% accurate, can anybody remember the actual probability that you have the disease?
Yes.
Yeah, and that was surprising, wasn't it? So 2%, right? And that was kind of really surprising. Now, I talked you through a kind of intuitive way of thinking about it. So literally thinking about what 0.1% means 1 person in 1,000, and also thinking about what 95% accurate actually means that 95% of people are told they have the correct result, 5% of people are told they have the incorrect result, okay? And then it worked out to say, well, hang on a minute, what was 1 in those 51 people? What's the probability of being 1 in those 51 people? And it came out to 2%, okay? Now, if you didn't quite follow that, it doesn't matter, because now we have a new way of working with it. We have a new way of working with it. So follow this through with me, okay? So let's think about this situation, but being applied with Bayes' theorem, with being applied with Bayes' formula, or Bayes' rule, okay? So first things first, I'm going to draw myself a tree diagram, okay? So my first, my prior, if you like, my prior belief is either you have the disease or you do not have the disease, yeah? So that's my prior belief. You happy? Now, what's the probability that you have the disease? Exactly, that's your prior belief. That's what you knew at the start, okay? The probability you have the disease is 0.1%, which then means that the probability you don't have the disease is 99.9%, right? It's got to add up to 100%. You either have it or you don't. These are exhaustive events, okay? In other words, they have to add up to totality, okay? All right, so then you go away and you get some more evidence. You go away and you get a likelihood. In this case, what is our new evidence?
2%.
That's not the new evidence, that's the posterior belief. What's the new evidence? Yeah, you go away and you get the test, right? That is your new evidence that you're achieving. Because before you had the test, you knew that your chance of having the disease was 0.1%, okay? Then you go away, you get a test, you get that new evidence, right? And therefore, you can either test positive or you test negative. So let's suppose you have the disease. Test positive, test negative. So what is the probability of testing positive? 95%. And the probability of testing negative is clearly got to be 5%. Okay? Why does it make sense that it's got to be that way round? So why has it got to be a 95% chance of testing positive for this first branch?
Because you already given that you have a disease.
Exactly, okay? So if you have the disease, the chance of you testing positive, that's an accurate result, okay? So if the test comes back as positive, it means that the test is correct. Does that make sense? Which means that the test is 95% accurate, which means that you must be one of those 95% of people that get the correct result, okay? Whereas if you have the disease and it comes back as negative, then you're one of the 5% of people that get the incorrect result, okay? Because it should have come back as positive, okay? Likewise, for the second set of branches, so let's suppose you don't have the disease now, what's the probability of testing positive? So if you don't have the disease, what's the probability that you test positive? 5%, because that's an inaccurate result, isn't it? So it's incorrect result. Whereas what's the probability of testing negative? 95%, because that's an accurate result. You don't have the disease, therefore you should test negative. So that's 95%, okay? So let's see if we can apply Bayes' theorem here, apply Bayes' rule here, okay? So I want to work out what is the probability that I have the disease given that I've already tested positive? I gave you that information, right? The test came back as positive, okay? So this is effectively what we need to find out. I want to find the probability that we have the disease given that we test positive. Probability we have the disease given that we test positive. So following Bayes' theorem up here, I am basically saying that event A is that we actually have the disease. And event B is that we test positive. Does that make sense? Yeah. And then I just fit the relevant thing in the correct place in Bayes' theorem.
Shouldn't B is don't have a disease? So A is having a disease, B is not having a disease.
This was a slightly different situation because I tried to make it a little bit easier for you because it's the same situation, okay? But here, because we've got two different events happening, we've got whether you have the disease first and then what your test result is.
Still unconditional? Or like...
Still conditional. Still conditional because one thing happens before the other. Yeah?
Test result?
Exactly. So whether you have the disease first, then what your test result is. Because you do the test after whether you have the disease or not. Does that make sense? Kind of? Think about it a little bit more. It will make sense, okay? So all I basically need to do, if I'm saying that A is that I have the disease, let me create some space. So I'm saying that event A is that I actually have the disease. And I'm saying that event B is that I test positive. Okay, is that I test positive. Now, according to this formula here, probability of A given B, so the probability that I have the disease, I'll do this in black. So the probability of A given B, in other words, the probability that I have the disease, given that I test positive, should just be, according to this formula, the probability of A, in other words, the probability that I have the disease, multiplied by the probability that I test positive, given that I have the disease, in other words, the probability of B given A, all divided by the probability that I actually test positive. Does that make sense to everyone?
So can you repeat the question? What was the probability that you are tested and...
So remember, the question was, what is the probability that I have the disease given that I've already tested positive? Because I told you that my test result came back as positive.
B given A.
So probability of A given B, because I'm saying A is that I have the disease, that's the chance that I actually have the disease, and B is the chance that I test positive. Yeah? So what's the probability that I have the disease given that my test result came back as positive? That's what the question which I was asking at the beginning. Does that make sense? So therefore, that should be equal to, by Bayes' theorem, the probability that I actually have the disease, multiplied by the probability that I test positive given that I have the disease, divided by the probability that I test positive. Is that okay? Right? So then it's just a case of working with this tree diagram to work out what's happening. Okay? Now, just be aware. This part here, the probability of B given A, in other words, the probability that I test positive, given that I have the disease, that's the hardest thing to work out. Okay? Because a lot of the time in real life situations, this is more difficult to find. Okay? This is difficult to find. It's basically based on a guess. So I call that my prior probability. Okay? This thing here, the probability of B given A, the probability that I test positive given that I have the disease. Because of course I don't know that. I have to work that out. So it's based on a guess. Okay? Now, in this case, I think we can make a little bit of an assumption. Okay? So, what is the probability that I have the disease? Sorry? Yeah, 0.1. 0.1. Sorry, I got the wrong way round. I said that was my prior probability. That's my prior probability. Okay, the probability that I have the disease. That's what I start off with. Sorry, I got that the wrong way around. Does that make sense? Okay, because that's what I said at the very beginning. That was your prior belief, whether you had the disease or not. Okay, so that thing there, the probability that you have the disease is based on a prior probability, and usually it's based on a guess. Now, in this case, we can streamline this slightly because I actually know the initial prior probability. I gave that to you, didn't I? What's the probability that I had the disease right at the very start? It was 0.1%, right? Okay? Then I'm going to multiply that by the probability of B given A. It's the probability that I test positive given I have the disease. Let's have a look at our tree diagram. Would you be happy that the probability that I test positive given I have the disease is that top probability there, the one I've circled? Does that make sense? Yeah? So in other words, I should multiply that by 95%. Okay? Then I need to divide that by the probability of B. In other words, what is the probability that I test positive? Are you happy that there are two ways that I could test positive? What are the two ways that I could test positive? Absolutely. So either I have the disease and I test positive, or I don't have the disease and I test positive. So I've got to consider both of those situations. Okay? So what is the probability then that I test positive? Well, let's think about this. What's the probability that I have the disease and I test positive? I just multiply 0.1% by 95%, wouldn't I? Yeah? And the same thing, if I do probability that I don't have the disease and I test positive, I multiply 99.9% by 5%. Okay? And that's what goes on the denominator of my fraction. That's what goes on the denominator of my fraction. Okay? Now, if we calculate that, so in other words, if I do, where's my rubber gum? So if I actually go ahead and calculate that, I say on the denominator, just testing positive, it's going to be 95% by 0.1% plus 99.9% multiplied by 5%. Okay. If you stick that in your calculator, lo and behold, it comes out as the 2% which we came up with yesterday. Does that make sense to everyone? Does that make sense?